All right. Now we continue on another example. 8-piece puzzle. Again, a toy example. If you well, I think you should be familiar with this simple puzzle. With the simple puzzle, we have these squares, numbers on them. They can slide if there is open space, and you have 9 of them and only one location to move. So, for example, here I can move either tile number 5 to right, or tile number 6 to left, or tile number 2 to down, or tile number 3 up. Okay, I want to design an agent to solve this problem for me. But before I have to define my problem, what is the problem to run a proper search for it. So, problem. States. The state describes the specification, the location of each of the 8 tile and the blank in one of the 9 squares. So state will be, for example, here, in this case, for example, on the left-hand side, the state is you have 7 here, 2 here, 4 here, 5 here, empty space or blank one, 6 here, 8 here, 3 here, and 1 here. That would be one state of the problem. The location of each of 8 tile and the blank is one of the 9 squares. Initial state. Any state can be designated as the initial state, not that any given goal can be reached from exactly half of the possible initiate states. Okay. Actions can be left, right, up, or down for each square, providing there is a space next to it which can accommodate the tile in it. So move will be doable based on available space. Transition model. Given a state and action, this returns the resulting state. For example, if we apply left to the start state in figure 3.4, the resulting state has the 5 and the blank switched here. So if I go left here, blank will be here and 5 will be here. That would be a new state, transition from current state to that state. Goal checks whether the state matches the goal configuration. Whatever configuration you define, normally we define a configuration like this, having these tiles in order from 1 to 8. And cost, each step costs 1. So the path cost is the number of steps in the path. So with for example, if you want to do the most efficient one, you have to do it with the minimum number of steps. It turns that this simple problem is NP-hard. Okay, for n puzzle family, if you have something like this with size of n, it will be NP-hard. Do you remember what was NP-hard? In the definition, the first session I was talking about Turing definition of solvability, and problems can be solved with non-polynomial order of just actions, let's say, the program. So NP-hard basically in plain English means very difficult when n increases to large number. All right, sorry, before doing that. So any question? Here I'm not solving the problem. I'm just saying that how we define a problem for different tasks if you want to design an agent for. Let's have a look at another problem. and see how is it. The 8-queen problem in chess. 8-queen problem in chess. Well, I hope you're familiar with chess, basically, at least. In chess, we have 8 by 8, you know, A, B, C, D, E, F, G, H, and well, depending on where you start from one side to other, 1, 2, 3, 4, 5, 6, 7, 8, 8 by 8, so 64. The queen problem is one of the very, very famous toy problems in AI. Is if you have 8 queens, how can you put them on the chessboard in a way that none of them can kill any other one at next move? Okay, how? So you know that queen moves this way, and this way. So this is a wrong answer, right? That queen can kill the other one. Or, you know, this one, I'll change the color. This one, there is no other queen here. There is no other queen here. There is no other queen here. So this one is in right place, and so on. You can continue that on all of them. Well, number of solutions and solutions, how can you do that? Well, it's not difficult. You can do it. It's easy. Well, basically, since I have been playing chess for years, so easy way to do it. You start from one, go L shape to the other one, to the other one, to the other one, to the other one, which falls here actually. Oh, sorry. I'm sorry, which falls here actually. One L. Yeah. And then again L, the other one should be here, and you have the other one here, but this one is in wrong place. You have to find another place for that. Okay, so but why this one is not working? Anyway, let it go. I don't want to get involved in back to chess. Anyway, so this is a problem, how to arrange these queens in the board that they don't kill each other. So the problem definition for an agent will be any arrangement of 0 to 8 queens. Okay, 1 to 8. Sorry, 1 to 8 queens on the board in a there is a state. Every arrangement will be in a state. Initial state, no queen, and action, add a queen to any empty square. Transition will be returning the board with the returning board. Sorry. What happened? All right. Okay. Returns the board with the queen added to the specification. So when you're at the situation, by adding next queen, a new board with an extra queen will be returned. 8 queen are on the board. None of them attacks any other. None of them attacks any other. So that will be the goal. And as I said, well, this is, yeah, this is it. Most likely, I think you should start from here. This one is wrong arrangement. If you start from here, 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 and you can start from yeah, here there will be another one, and another one. I have 7, and the 8th one will be, I think I missed the 8th one. Okay, yeah, anyway, I don't know, still. And some other example problems, more practical one, are these lists. I'm not going into these problems, but just introducing, giving you hints on how this problem look like. One very, very famous problem in AI and in computational complexity is traveling salesperson problem, TSP. Traveling salesperson problem. It says a given in a map similar to our Romania map. The problem is a Turing problem in which each city must be visited exactly once. not less, not more. So I give you a map similar to a Romania map. I tell you, find a way to go through every city, but only once, not more than that, not less than that. So that's a very famous problem, and AI, and it relates to many other, practical problems. Many other practical problems can be reduced to travel salesperson problem. It's a famous one, started by Euler, I think, like that. VLSI layout problem, integrated circuit layout problem. This is a very, very important problem in IC design when you have many components. We are talking about millions or even billions of components on one integrated circuit. And integrated circuit, they are not completely planar, but you have only few layers of wires and wires to come out. So place and route means I have a board. I want to place different components on it, and they need to be connected to each other, but at the same time, well, there is a problem of limitation of number of routes, limitation of space, limitation of number of layers. That's an NP-hard problem as well. And the routing and placement is a problem which AI can help with. Robot navigation. We have done robotic together. We know that robot navigation itself is a problem, considering the input and output of the robot and possible movements and kinematic of the whole system. That is another problem in which a robot can move in a continuous space with an infinite set of possible actions and states. Automatic assembly sequencing, another problem in which the aim is to find an order in which to assemble the parts of some object efficiently, to the best way, how to order the sequence of the assembly. The other one is protein design, for example. Another one, the proteins are kind of, well, you can think of like jigsaw data. You connect them together to build bigger protein, in which the goal is to find a sequence of amino acids that will fold into a three-dimensional protein with the right properties to cure some disease. I don't know from, I'm not very familiar with details of this, but this protein sequencing is also an application which I see many AI people are working on. Any question? No question? All right, very good. Do you know any other problem? Just to introduce here. No? Robot assembly, for example, I have it here. The state is real valued coordinate of the robot joint angle angles, parts of the joint, and the object to be assembled, inputs of the states. Actually, you can define a state. It's a large state space, but still definable. Initial state, the rest configuration. The robot is in home position or rest configuration. Action, continuous motion of robot joints. Goal is complete assembly, complete the movement from the beginning to the end, and path cost, time to execute plus energy to use, and probably with some other constraint we have in robotic. This is an example. So, okay. So any questions so far? Because I'm switching the argument to search itself. No question? Very good. Searching for solutions. Oh, this is again, all right, okay. Oh, thank you. Searching for solutions. Having formulated the problem, so far we learned how to define a problem. And now we understand the concept of solution. So we have concept of problem, we have concept of solution. Now among state space and all possible solutions, I want to find one specific solution, want to find a solution. among all possible actions, sequence of actions in the state space. A solution is an action sequence. So search algorithm work by considering various possible action sequences. The possible action sequences starting at the initial state from a search tree. This is a new concept, search tree. With the initial state at the root, so we put initial state at the root. Well, my slides are frozen again for you guys. Let me stop that and restart. No, Blackboard is frozen again. Sorry, if you hear me, I need to again re-enter to the Blackboard. I don't know how many times. Okay, I need to re-enter. Start with the basics of the search. You know, here our solution is very basic and naive, but this is the base of all other algorithms. We start with the search tree to map our problem into a search tree to another data structure, to another configuration in which we can see our options after each set of choices. The branches are actions, so we define something called search tree. Root of that search tree is something like this. We start from one root, then we go for choices. We have choices at each node. So from there, we might have extra options and so on and so forth. We build up a tree of possible actions at each state down to other states. So actions are the branches, nodes are the correspond to the states. So states fall here, and the state space of the problem. To achieve the goal, to achieve goals, or to maximize our utility, we need to predict what the result of action in future. So if I take this action, I'll get to this state, and I have two other options to go, and from here I have other options to go, and so on till we get to the lowest level of our tree, which are leaps of our search tree. There are many sequences of actions, each with their own utility. We want to find or search for the best one. So, for example, again, I'm defining my problem, okay? On a holiday in Romania, currently, we again back to the Romania, and our agent is at the moment at Sidi Arad. Flight leaves tomorrow at Bucharest. So goal is be in Bucharest, formulate the problem state are various cities, action drive between cities or choose next city. That action. So find the solution is the sequence of, sorry. All right. Sequence of cities from, let's say, from this city to this city to this city to get to Bucharest. So sequence of cities to get us to the target. Again, the map, I want to start from here and get to Bucharest as our target. And so at this stage, I have three options to go. I'm sorry. Okay. I have to. At first, I have 3 options. So my tree will be like 3 branches. One branch here is Arad. The other branch will be Tim. The other branch out will be Zir. The other branch will be Sibyl. At Tim, I have only one option going here. At this one, I have again one only option going to Oradia. And here I have 3 more options going to other. So we build up a tree, and search is defined over the tree. Well, we have to just, well, we know this problem is static or dynamic. We should know it is observable, partially observable, unobservable from our previous chapter. Deterministic, stochastic, discrete, and continuous. We discussed that already. A problem is defined by 4 items, as we have here again redefined all problem. Let's have a look at yeah, and real world. I also explained in the real world problem is more complex, and states must be well, here we abstracted states in just one node. All right, so yeah, this one is the better one. The next figure shows few steps in growing the search tree for finding a route from Arad to Bucharest. Okay, at root node, the tree corresponds to the initial state here. This is my initial state. That's where I am. And I have different options to go to other cities. The first step is to test whether this is a goal state or not. So I'm thinking algorithmic now. So we are here. Question 1, is this goal? If yes, we're done. If yes, we're done. If no, we have to take action. We have to take action, all right? Then we need to consider taking various actions. We do this by expanding the current state that is applying each legal action to the current state, thereby generating a new set of states. In this case, we add 3 branches from the parent node. This is also a keyword, leading to child nodes, which will be these new nodes we are adding. And now we must choose which one, which of the 3 is possibility to consider for further. So next move will be this. So I have the 3, I'm picking one of the 3, and I have to continue on expanding my branch. So if you can see at this, I have different options, and here this I have different options, and this I have different options. So at this node, I can go back to Arad that we started from. I can go to other cities, and in this one as well. When I'm coming to this, I also have other options to go on, or continue on the same thing. So algorithm will be something like this. This is a pseudocode for the algorithm. It says you have a tree search problem, return solution or failure. You can find a sequence or a sequence of branches to get to the goal, or you say no, there is no way we can find it because it's an infinite loop, or well, sort of bad defined problem. If the frontier is empty, means the leaf nodes, the lowest level of nodes, then return failure. Means you have reached, you have traversed all 3 branches, you have checked everything, and you haven't found anything, so it's a failure. We couldn't find. Choose a leaf node and remove it from the frontier. If node contains a goal state, return the corresponding situation, and that you have found the goal. Okay. So graph search is the function we use here, and inside this function we go and check whether each branch is the goal. If not, move our action to the take the action and move to the other node. So the thing is, if the frontier is empty, then return failure. Choose a leaf node and remove it from the frontier, and if the node contains the goal state, return we found the goal state as a solution, and add node to the expanded set and continue on that. So building up the tree and searching inside the tree to find the solution. Each of these 6 nodes in a leaf node, that is a node with no children in the tree, the set of all leaf nodes available for the expansion at any given point is called a frontier. So frontier are the lowest level of the leaves we have. The process of expanding nodes on the frontier continues until either a solution is found or there are no more states to expand. Search algorithm all share this basic structure and very primarily according to how they choose with the state to expand next, the so-called search strategy. This is the next part which I'm going to talk about. Well, apart from the basic, building up a tree and checking branches and nodes of the tree, how to do that, where to start. Let's say I have my tree. So I have the tree. Now I'm trying to find the solution. How to do it will be the strategy, which I'll talk next. One thing which we have to be careful are loopy paths. So the complete search tree for Romania would problem like infinite if we fall in a loop. If we go to a city and we go to another one and we come back to the original city. For example, here in here. So if I go here and I go here again, so means I'm continuously going around and round between 2 cities, and I never get out of that loop. That's a fail. So we have to consider these kind of situations, and we call those loopies, and will give us an infinite actions which never get to anywhere. So this can cause failure in my search, and we have to find a way to stop that. We have to find a way to not to fall in those kind of difficulties. Loopy paths are a special case, more general concept of redundant paths. So paths which are useless, and we have to consider those in our search strategy next. And same thing as I said, we are expanding this. This is the map, and in the tree build-up, what we do, we go through these nodes and branches to figure out how to have the tree for the search. Okay. Root finding on a rectangular grid, like used in the next, is a particularly important example. This one. Okay. As another problem, as a more general problem. So if I go from here, if I want to move from one state like this to other, I have 4 choices. Okay. At this one, another one, if I pick the other one here on B, if I don't want to go back, I still have 4 choices, but for it to other one, and so on and so forth. It can go over and over and build up a big problem. It can build up a big problem. In such a grid, each state has 4 successors. So as a search tree of depth D, means if you want to go D levels down in the tree, that includes repeated state, has 4 to the power of D leaves. But there are only about 2 times 2 to the D distinct states. Okay. within D steps of any given state. For D equal to 20, so dimension of D equal to 20, this means about 1 trillion nodes to search, but we have only 800 distinct states. So look at the problem again. Because it's true, because when you're moving and it happens, game design, we have many of these. So you have four, if you go on for dimension of higher dimension, and number of possible branches in your tree grow very, very fast exponentially with the number of choices. You have 4 choices at each step, and if you go depth of D means D level of choosing and branching, you will get 4 to the power of D leaves. So your problem starts with 4, then this one with 4, this one with 4, this one with 4, this one with 4 again. So each one continues with 4, and so on. So after 20 layers, just first, second, third, after repeating this 20 times, you get billions of nodes. Your tree grows huge, in a huge size. But the total number of states in this case is only 800. Because you have a lot of redundant the paths. So a lot of turning around, just repeating the same thing. If you do it blindly, if you do a blind search, if you do what we call an exhaustive search. Thus, following redundant path can cause a tractable problem to become intractable problem. So if I make a mistake in choosing right strategy, a problem which can be solved easily will turn to unsolvable problem. And this is true even for algorithm that knows how to avoid infinite loops. So algorithm that forget, so this is a famous say, algorithm that forget their history are doomed to repeat it. So that's why you need to be more careful with designing the agent. Searching algorithm requires a data set to keep track of the search tree that is being constructed for the n node of the tree. So if my tree has n node, we have a structure that contains the problem of n states and parents, and action, and n cost paths for each one. For the 8 puzzle, for instance, for what we had, you see we have 4 branches at this situation. I can go to this by moving 2 down. If I do down, I can move to this. If I do left, I can come to here. If I do up, I will be here. If I do right, and so on. You see, you can continue that more and more and see how many different options you have for each movement. This is a tree of your options, and search is the next step. When you have your problem, you build up your tree, and the role of the search is going through the tree and find the best solution. If you say it doesn't make sense to you, I won't accept that, because when I ask you to find the best path from on the map from Arad to the Bucharest, actually unconsciously you built this tree or something like that in your brain to calculate different choices, different solutions to find the best way. You remember when I said find the minimum, what did you do? You just pick different options. Okay, if I go from here to here, if I go here to here, I'll find it. But the key point in your brain is you know how to eliminate redundant branches. If you go from CDA to CDB, you don't think going back to CDA. So you're definitely canceling a lot of options. But our infant level agent, our Very naive agent needs to be told not to do that. So similar thing for the vacuum cleaner. For the vacuum cleaner, the branching up. So if you're at this, if this is the root, you have two options. Either go right or go clean, suck up. Okay. If you have that, if you choose this, you get two options. You either if you clean up at this level, right, and okay, so it goes here, and from here you have if you clean this, you end up to this one. This is the goal. You don't have that goal. And if it's right, you go to right, it moves to right again at this. If you go to left, you come here, which is a loop, useless. If you say clean, it will clean that. If you move to left and do same thing, it will be the goal. If you end up, the other one is clean, and you can see the branches of this. This is not the complete one. This is not the best one, but shows you the branches between left and two options of the vacuum cleaner, and you can build up a tree, decision tree, or for a search tree, sorry, for this agent. Search strategies. Any questions so far? So what we did. Let me summarize what we did before I go to the next. What we did. First, we defined a problem and solution. We said, what is a problem? What is a solution? And our problem was, actually, the next question is how to find a solution. So I know how to define my problem now. I know how to define my solution now. And I know what does it mean. I have to search for the solution. To do the search, we focus on a search tree. Search tree is a sequence of actions and options we have in the state space of the problem. In the state space of the problem, we have to search for solutions. And doing search, we have to build up a tree, search tree for that. So to do this search on the tree, there are options. As I said, it can be uninformed or informed search. Okay, we have to do that. So strategies for search are evaluated, therefore, by if the search is, if the algorithm, if the strategy you're suggesting is complete. Complete means it definitely, if there is a solution, it can find the solution. That means your search strategy is complete. Does it always find a solution if one exists? The other one is time complexity, means number of steps you need to take to find the solution with this strategy. Lower, better. Space complexity means maximum number of nodes in memory, means how much you need to remember to get to the solution. So we call that space complexity. So time complexity and space complexity is the maximum number of nodes in memory. How many nodes you need to keep in your computer memory to get to the answer. When I give the examples, you see. And optimality is, does it always find a least cost solution or not? If a search can find a solution and that solution is always kind of minimal cost, we call that optimal search. Search strategies, the time and space complexity, measured in terms of, well, maximum branching, factor of the search tree, depth, how many levels I need to go down to find, and maximum depth of the stage. So B, D, and M. Remember these parameters. We use these parameters in our next search strategies introduction. Search consider, okay, this is an example. Any question? Any question? All right, so I want to start the other one, at least as an introduction. For next week, we are ahead. Okay, no, I have to cancel this before I do anything. Squad. Very good. Going back. No. Well, okay. Talking about search strategies, first we look into uninformed search, in which we are not making any assumption, any extra guidance from outside for our search. We look into 5 search strategies. One is BFS, or breadth first search, DFS, or deep first search, iterative, uniform cost, and bidirectional search. Okay, uninformed search, while searching you have no clue whether one non-goal state is better than any other. Okay, we don't have any overall evaluation of everything. I don't have any guidance. So when my agent is in one of the cities, the next step is taking is based on just very close information he can see. It doesn't have any general guidance from with bird eyes, let's say. Your search is blind. You don't know if your current exploration is likely to be fruitful or not. Various the blind strategies are, as I said, BFS, UCS, or uniform cost depth, DFS, and iterative depth. Okay. Breadth first search, BFS, is the simplest strategy in which the root node is expanded first, then all the successors of the root node are expanded next, and then their successors, and so on. In general, all the nodes are expanded at a given depth in the search tree for any node, at the next level are expanded. It has a first in, first out approach. A new node, which are always deeper than their parents, go to the back of the queue in the search queue. So I give you an example just to show how it works, and that example, I hope, make it clear that how we do search. So let's say my problem, whatever problem it is, can be the vacuum cleaner, can be 8Queen, can be the puzzle, or others, will be expanded in a tree like this. So the decision I have to make needs to go through different states to find the right sequence. So expand the shallowest unexpanded node. So here I start from this node. I expand that, means I have 2 options, either this one or that one. Okay, with this at step 1, we are at this node. Is this goal? If yes, we're done. If not, go to the next. Go to the next node. Where is the next node? Lower level first. Lower level first. So node waiting in queue to be expanded. So when I'm here, the next node to be investigated will be node B and node C. So check node A. Is it the solution? No. If not, go to this one, B. So check B. When you are here, the next node of B will be D and E. So I add them to my queue. So B is already under an investigation. So will be C, and I add D and E to the list, but still not there. This is the queue that I was talking about. This is the first in, first out. Whoever comes in first will get out first of this queue. And this is the memory size I was talking about. You remember I said time complexity and space complexity. This is the space complexity, how big your memory need to be. This is a simple example. I have few nodes, so it wouldn't be a big issue, the size of the queue I have. Okay, at each stage, the node to be expanded next is directed by the marker. So here, as you can see, first we check this one, then we check this one, then we go check and this one. So these are checked already. And when we did this one, then will be D, the next one. So at here, I'm checking C. So my queue is D, E, and F, and G will be on my list to be checked next. When I get here at D, I'm checking D. So my list will be E, F, G, and childs of D. I don't know, I can't see them here, but whatever children it has will be in my queue to be checked. And you can see when you are going down, this queue might expand larger and larger. Let's have a look at this example. I do this example and let you go. Okay. We still have time, but I don't want to continue. So when we initially start, we start from this node. This is the root state. So question is S the goal? No. So S is not goal. So we are investigating on S. Is S is the goal? No, it's not the goal. So who is next? Who are next? Who are children of S? Children of S are A, B, and C. Here, I'm making an assumption. We go by just per assumption that we go from left to right. It doesn't make any difference. You can do it from right to left, but this is a kind of general agreement. After S, so S is checked. Checked. It's not the solution. So I go for children. Children are A, B, and C. So when I'm checking S, I know that next one in the queue will be A, B, and C. You see A, B, and C. These are next in my list to be checked if it's not S. It's not S, so I have to go to A. I'm checking A. When I'm checking A, who is in my next list? So I keep B and C from previous step, and I add children of A as well. So will be D and E to my checking list. So if it's A, if it's not, continue on your list. So you see here is probably is better. You see S will be checked, A will be checked, B will be checked, and when I'm checking B, I have to add B's children, which is only one, which is G. G will be added because G is children of B. So is B the goal? No. If not, check the next one in the queue. Next one in the queue is C. And bring in C's children, which is F. So F, sorry, F will be added to the list. It's a child of C. Is C the solution? No. Go to the next one. Check D. And bring in these children, which is H. So H is child of D. So D, is D the solution? No. Check the next one. E. And bring in child of E. So child of E is G. G is already in the queue. I'm not bringing that. That's why we don't need to bring in anything, add anything to our checklist. Okay, so is E the solution? No. Go for the next one. G. Is G the solution? Yes, we found it. After how many steps? 1, 2, 3, 4. After this number of steps, and you see the Q size also is maximum. We had like 3 children in each level, and we went to like maximum 4 components in my queue, in my frontier list, in my checklist to be checked. So it was E and found the goal. Any question? No question? Everyone is happy? Okay. So if everyone is happy-ish, so this search, is this search complete? Yes, this search is complete. If you have an answer, you will definitely find it. How much time it takes? The time complexity of this method is order of b to the power of d plus 1. So number of, you remember b, m, d. You remember those? b, m, d in the previous slide. If you remember, I said b, I just write it back for you. Okay, b is the number, sorry, b is the branching. Branching factor. M was the maximum depth, and D was the depth, maximum depth and depth we have. So with the number of branches, it's in the order of B to the number of branches to the power of depth, which is large. Okay, this number node will regenerate. So we can say this is a rather complex algorithm. So space, how much memory you need. Keep every node in the memory, either in fringe or in path or in fringe. Okay, so the order for space is also b to the power of d. Is it optimal? Yes, we guaranteed that deeper solution are less optimal, so we can find that. In terms of space, is the bigger problem more than the space in this case will be a problem to keep everything in memory. So for example, just to see how much this takes to find a solution, with the depth of 2, with the number of nodes, number of 110 nodes, the time will be this much. It takes on a computer, with explained here, explained down, and it needs 107 kilobytes. For 4, depth of 4, number of nodes will be 11,000, 11 milliseconds, and it needs 10 megabyte memory. For 6, depth of 6 means 6 level going down, with number of branches of 10, okay? Number of branches of 10, it will be 10 to the 6, 1 million nodes you need to keep, and you need 1 gigabyte memory and 1 second time. If I go down, like in 16 level, depth of 16, the number of nodes will be 10 to the 16, and it takes 350 years to find the solution, and it needs 10 exabyte to save that information. So which means practically impossible to do it with this algorithm. So this search algorithm as a blind search is not a good solution for many practical options in which you have higher depth, a larger number of branches of solutions. Probably for toy problems will be good, but not the best for other sort of solutions. Okay. Yeah. And there are other algorithms as well. I'll talk about them next week. Any question or anything you want to talk about now? I'll stop recording. we continue this